All right, so let's talk about limits. I said before that limits are the underpinning of calculus. Let's go ahead and write that down real quick. Underpinning of calculus. And we know that calculus is one of the greatest achievements of humanity, right? I said that, I stated that, it was bold. And so limits undergird this entire idea. So they must be really important. But at the same time, I feel like they don't make a lot of sense to students right out the gate. We're not able to tell, why they're important or different in any way. So that takes some time, is what I want to say. Kind of think in the long run about these things, long run understanding. Because while it is a relatively simple idea, it's also kind of subtle. And coming from algebra, it just might not make a ton of sense. So the biggest thing I want to draw your attention to is the difference in this notion of being approaching and not actually what the function is at. Okay? This helps us get around the paradoxical nature of measuring instantaneous velocity. So we'll see that towards the end of the lecture. But the idea here to focus in on is a limit means approaching. That could be long run or short run, like towards an instant, what we're approaching. So not the function's actual value. So one way I like to say this is that you can see where I'm headed and where I end up are not necessarily the same thing. Often they are, right? Headed to work, I end up going to work. Sometimes I'm heading to work, and at that last second, I don't end up going there. And so this is the distinction between a limit and just seeing where a function is at a point. Okay, so I want to look at limits from a few different perspectives, and then I'll set you loose on working through some examples yourselves. So first of all, finding some various limits graphically. Let's take a look here at this graph. So we've got this function f of x. That is clearly not what we say a continuous function. It's got some jumps and gaps and holes in it, which is fine. But I want to highlight what limits mean in this context. So let's take a look at something that's pretty standard. How about the limit? And we'll use this notation. We're going to ask, what is f of x approaching as x approaches, let's say, 2. So the way we think about this is, all right, I'm going to approach the x input of 2. Let's start coming in from this side. You can kind of think of like being an ant on this line, or like a better idea is like a slider, like a volume slider to the right. And as I slide towards 2, what is my function f of x sliding towards, if anything? It doesn't always have to be. So as I slide x towards 2, we see that the curve f is approaching this value of what? Y equals 1. Okay? And importantly, we can do that from both sides, right? If my volume slider was higher than 2 and I slid it towards 2, what do we see is happening with the curve f? We'd be sliding down on the curve, again towards y equals 1. So what we say is that the limit appears to be and we're just saying appears because it's a graph, so it's not perfect information, but the limit appears to be, we'll say L equals 1, okay, or y equals 1. Either or is okay. So again, I'm not asking what is f of 2, right? That's a different question. If I were to ask versus what is f of 2, we know that f of 2 is 1 just from looking at the graph. You see how this is a different question, what I asked? What is f of x approaching was the question. Okay. So let's look at something that maybe draws a distinction between the two a little bit clearer. Let's see, what is f of x approaching as x approaches 3? Okay, so again, we kind of come in on this x-axis. We slide our dial towards 3 and see what is the corresponding action on the curve. All right, so not so much exactly what the point is over, but what is happening on the curve as I move to the right towards 3 with x? Well, it seems like f of x is heading toward what? Well, it's heading towards this hole, which is at a height of y equals 2. And the same thing, if I move my volume slider back from 4 to 3, we'd be coming in on the curve here. The curve would be responding with outputs up here heading toward this hole of y equals 2. So f of x is approaching y equals 2 as x approaches 3. I'm going to give you some notation so that we don't always have to write out this storyline every time. And we'll be using this throughout the rest of the course. And you've probably seen this before, honestly, but the notation is that the limit of f of x as x approaches 3 is equal to 2. So again, noting that this is the y value, or the output, and this is the input. So this is how we say that the limit of this function is heading to 2. Now your alarm bells might be flaring off. You say, well, that's not where the function's actually defined. There's a hole here, right? And this is the point of this exercise here. The function is actually undefined at this point. Well, it's defined, but it's not defined to be at 2. Let's say that. At this point, there is no input-output pair. The function isn't equal to 2 at this point. What's it actually equal to? Well, it's equal to 3. Okay, it jumps up. So you can kind of think of like when the, your postage jumps up when it goes from 34 grams to 35 grams or whatever it might be. There's this bump. Same thing here. There's this bump. So we say this even though f of 3 is 3. So again, this is the difference between approaching versus being at a point. Okay. And lastly, what I want to do with this graph is highlight the notion of one-sided limits. Okay, we say for a limit to exist, okay, again, which means that we agree that the function is actually approaching a point. The limit, we say the limit from the left, so where it's approaching from the left, and limit plus limit from the right, must be equal. Okay, so that was the case here. We saw that the function was approaching from the left, it was approaching y equals 2. And from the right, it was approaching y equals 2. Okay, so that limit exists, and it is the same value from the left and from the right. Okay, so I'm going to clear this out real quick so we can look at something where that doesn't happen. Okay, so the example we'll look at lastly here is, and I'll use our new notation, find the limit as x approaches -1 of f of x if it exists. Okay, so again, it's not always guaranteed to exist. So that's something that's also possibly new for us. So we need to always consider that as a possibility. So let's come back up to the graph and take a look. All right, so as we move our x slider to the left, so this is actually our left-hand limit as x is approaching -1, what do we see is happening in the graph? Well, f is approaching y equals 3. Okay, so actually let's write that down using our notation. So we see that the limit as x approaches -1, and I'm going to use this negative superscript notation to say, hey, we're coming at it from the left-hand side. Okay, that's all that means. F of x, this appears to be 3. Okay, y equals 3. And so now we want to take a look and see when I move my volume slider from the right, what do we get? So as I move towards -1 from the right, what is f of x approaching? Well, it's approaching y equals 2. Okay, so that's a different value. So again, you've got this kind of break discontinuity in the function. You can, again, think of it as a jump between costs of things, or, you know, if something like received an impulse, like something got smacked with a hammer, and this is a position function, then it got, you know, jumped from point 2 to point 3, whatever it might be. Here we say, hey, the limit is not the same from the right and from the left. So we say limit from the left is not equal to the limit from the right. Therefore, the limit doesn't exist. Okay. So this is a case where we need to be careful and note when something it doesn't have a limit. And this function is defined at f of -1, right? At f of -1 is this dot here at y equals 3. Okay, so it's defined here, but it does have a discontinuity, and the limit doesn't exist. Now, you might be asking yourself, why are we caring about such things? Again, remember, I want you to think in the long run about this concept. This underpins all of calculus. But essentially, we need this to work on functions that we care about in order to take us from average velocity, average rates of change, to the instantaneous rate of change. We need to be able to zoom in on functions and have things work out in terms of our definitions of how we measure change. So if there's breaks like this, we have to be aware of it. Okay, if there's holes like this, we have to be aware of it and deal with them in specific ways. All right, so this is the graphical view of limits, one-sided and two-sided limits. If we have a jump at a certain point, we know the limit's not going to exist. But here, again, I'll maybe quiz you guys real quick on this. I'll ask you, what is, if it exists, the limit as x approaches -2 of f of x? So this would be a good chance to just hit pause on the video and think to yourself and convince yourself, what is the limit, if it exists, it might not, as x approaches -2 of this function? Okay, and so I'm assuming that you've paused it and thought about it. So again, as I approach -2 from the left, f is approaching y equals 2. As I approach -2 from the right, f is approaching y equals 2. And so that's all we need to know, right? The fact that the function isn't defined here, there is a hole, doesn't matter in terms of the limit. So the limit is actually equal to 2. All right. So that's the graphical perspective. Let's look at some of the other perspectives we have. So here we have a table. Okay, use a table to estimate this limit of, as x approaches 1, of 5 plus the natural log of x. Okay, so there's actually a typo here. This is interesting. So we don't need this y equals. That's not the same. It's really limit of, this is the function here. So I don't know how that got popped in there. But use a table to estimate this limit. Okay, we can do that, and in a similar way that we did with the graph, we're going to look at it from the left and from the right. Okay, so I'm going to drop this into my y equals of either my TI-84 or my Desmos, and we'll take a peek there. Okay, so I've thrown this into Desmos here, and then I went ahead and created a table with the function. So I see the graph. Makes sense. It's a log function that's been shifted upward. And you can use this table feature to pop out a table here. So settings and then create a table. And in so doing, what I did was then created a table of values. Let's assume maybe you guys didn't have this. So let's do this. and start from scratch. So what we're trying to do is determine what's happening with this function as x approaches 1, right? That's this question here. So as x approaches 1 from the right and from the left. So again, think about turning up that dial from 0 to 1 on your input. Well, I could start relatively close and say what's happening at 0.9 and look at the output, and then scoot closer with 0.99, 0.999. Maybe let's go up to 4 decimal places. Okay. And you can see, and what's nice is it'll even plot the points on here. You can see we're approaching this y equals 5 value from the left. And from the graph, I mean, you can tell it's approaching 5 from the right too, but we're exploring this numerically, so I wanted to show you how to take care of this. So now we'll be coming in on our x equals 1 here as our input value that we're interested in, coming in on it from the right, so we'll start at like 1.1 maybe, and then move into 1.01, 1.001, 1.0001. We see we're getting closer and closer to 5. Okay, so it would appear from the left and from the right. Let's head back to here. So you could copy in this table here, you know, just what you had as your kind of proof or evidence of a limit. And so we see limit from the left appears to be 5. Limit from the right appears to be 5. Therefore, the limit appears to be y equals 5 as x approaches 1. Okay, again, the importance, since we saw in this example that approaching from each direction can change what's happening with the output, we need to note that here that the limit from the left and the limit from the right have been kind of accounted for. Okay, so this is using a table, and again, you can use Desmos or your TI-84 to just come in on whatever this point is, starting at, you know, that 1 plus maybe 0.1, and then 1 plus 0.01, etc., to come at it from the right. Oops. And then, you know, 1 minus 0.1, 1 minus 0.01, etc., to come at it from the left. So left and the right. Okay. So that's that process there. And then lastly, the final perspective on limits that I wanted to discuss, and this is something that we could go into a lot of depth on, but I'm really not going to, which is that we can find the limit exactly using the properties of limits and continuity. Now, we don't have all these properties yet. We're kind of just scratching the surface of limits and continuity. So I want to kind of put an X through this for the moment and say, let's just explore this thing and see what's happening. Okay, so we'll take the limit as x approaches 3 of x squared minus 9 over x minus 3. Now, if I were to graph this, let's actually do that. Let's get rid of all this stuff and say, all right, here's my f of x, and I've got x squared minus 9 in the top over x minus 3, right? Should look pretty simple. It's actually a line, and we'll see why that's the case in a second. But what do we know about rational functions? We have to look out for when the denominator equals 0. So at x equals 3, we have a problem. It's actually undefined, this function. Okay. Everywhere else, this function's okay, right? I plug in 4 billion, -7, 0. It's all okay. It's just when x equals 3 that we have an issue, right? So what we got to do is think about, well, at the point is a problem, right? But we're not talking about being at the point. We're talking about the limits. We're talking about approaching. So one thing we can do is use this idea that this is equivalent to, in the top, if I factor it into x plus 3 over x or times x minus 3, difference of perfect squares. Oop, I'm not on my graph here. So if I break this into its pieces in the top, x plus 3 and x minus 3, all over x minus 3. Well, since we are not actually going to 3, right? We're not actually using x equals 3 as a value. We're approaching x equals 3. Since that's the case, then we don't really have an issue, right? Because everywhere else, for every other x value, this function's fine. So what we can actually do is say, well, hey, since we're not using x equals 3, we can cancel out this, what we call a removable discontinuity. Because this is what? This is 1 literally everywhere else, right? When x is 10, this is 7 over 7. When x is 4 billion, this is, 4 billion minus 3 over 4 billion minus 3. So it's always going to cancel each other except at x equals 3, which we're not including. So this really does simplify the limit greatly to saying, well, then this must be the same as 1 times the limit x plus 3, since we're not including that pesky x equals 3. And so what happens here? Well, as x approaches 3 for this 1 times x plus 3, this function has no breaks or, problems with it. It's the line x plus 3. So this is really just 3 plus 3, which is 6. And if we go to the graph, we'll see that that is the case. So as x approaches 3, let's put in just x equals 3 here to zoom in. Right, we know that the function is undefined here, but we see where the function is approaching. It's approaching 6 from both sides. Okay, and so here we used the algebraic perspective, since we noticed there was a removable discontinuity here, to go ahead and evaluate it. Okay, so just because you have a value approaching something that makes the denominator 0 doesn't mean the limit doesn't exist. Here it actually did. Okay, so that's a big misunderstanding that I see frequently with students. So we just did an example of an algebraic approach, how to use a table to approach limits, and how to approach them graphically. So I hope this helps you frame your lab activities and your exercise sets, and I'm looking forward to your community problems as well. All right, we'll see you there.